got a whole bunch of kind of practice now sequencing up. So how many moles of oxygen react with 2.25 moles of nitrogen? Okay, so in this case, what are we solving for? What do I want? Well, what I want are the moles of oxygen. Why do I know it's O2 and not just an O? Does it say atoms of oxygen? No. So we know it's O2. Okay, another tip off, look at the chemical equation. It's showing us as O2. What was the given information? Well, we're technically given two pieces of information. We're given the green thing, and we're also given that purple chemical equation. Okay? That purple chemical equation gives us lots of conversion factors. We would have to know which ones that we want to use. Okay? So take a second, pause the video again, see if you can come up with your conversion process. Yeah, that would be the space bar again. Okay, presumably now you're back because you've come up with some process or you've gotten stuck and you don't know where to go. Okay, my argument again for starting this whole thing off would be to pick something that I know has to show up. I know I need moles of O2 to show up in the numerator. Okay, because that's what inequality means. So I would start with the moles of O2. Okay, am I given the moles of O2? Well, I could go up into my green box. That green box says moles of nitrogen. Well, what is the symbol for nitrogen? That would be N2, so that's certainly not O2. The purple does have O2 in it, okay, that purple box. The moles, yep, chemical equations give me moles or molecules or atoms, depending on what I'm looking for. Since I'm at moles, I could do this. The number associated with that, assuming this was a balanced equation, would be 1. So I could even put in a number there. Okay, but because it's from the chemical equation, it's not that I have 1 mole of O2. It's that I know 1 mole of O2 can be related to nitrogen or NO2. So I need something in the denominator here. Okay, I have to specify either N2 or NO. So if we wrote moles of NO, this is a valid conversion. Okay, and before you start saying, oh, I didn't write that, that's okay. Don't stress about that. For this conversion to work, what would then need to happen is I would need to introduce moles of NO, right? Well, am I given just the moles of NO? If we look back to the question, I'm not given just the moles of NO, I'm given the moles of N2. I do see NO show up in a chemical equation, and it is 2. But again, because it's in the chemical equation, it's related to something else. Okay, I can't just pull that 2 out. That 2 is intrinsically tied to everything else within that. So if I'm going to write moles of NO there, I would also have to write moles of something else underneath. Before we start going down that path, what I'm doing is undoing the work that I had just written in. If you find that you are undoing something that you've done, you probably shouldn't have done it to begin with. So writing the moles of NO was a bad idea. What do I want to write instead? Well, if moles of NO was a bad idea, then I'm not going to pick NO. O2 was already written, so that's off the table. That means I need to be using N2. Well, how many moles of N2 does it say I should use? According to the chemical equation, there's nothing written in front, so it's a 1. I know the moles of N2 would need to cancel for my equation to work out. Am I given just the moles of N2? Yes, sure enough I am. I'm given 2.25 moles of N2. Now I can establish that all I have to do is the math now, multiply 2.25 times 1, divide by 1, and I get 2.25 moles of O2. Okay? This was a trivial solve. They were all 1s, so it didn't really matter. Okay? But this is also a single conversion. What happens if you have to do 5 or 6? Okay? It becomes difficult to track if you're just jamming numbers in. If you write down your units appropriately, both the measurement and the substance, you can track where you are at within your calculation, and you can ensure that you don't miss things. Okay? What would go in the denominator under the green? Just a 1, because again, that was a single piece of given information. I don't want to alter it. Okay? Your textbook, because this was a textbook slide, gone through, shows the exact same work, but now it shows it all as one piece. So again, the piece, the final solve, isn't useful for you. It is what is the process that you're using to place that information in. Okay? So make sure you're considering that when you go through to establish these solves. So here's an equation again. We could go through and try and set up some questions. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Okay, there's a lot of text. I want moles of CO2. Okay, and I'm given 1 mole of sodium hydrogen carbonate. I'm also given the chemical equation. So what information do I choose to start with? Okay, and again, that's personal choice. I'm going to choose to start with the purple chemical equation because I know I need moles of CO2. What do I want to relate those moles of CO2 to? Because the chemical equation is not an individual piece. It's a relationship. That relationship has to show up as a fraction or a conversion factor. Okay? It can't show up just as a single piece of information because that entire box is not a single piece. It has, in this case, 4 pieces. Okay, what do I want to relate it to? Well, I think relating it to moles of sodium hydrogen carbonate is going to make sense because the given piece of information is just sodium hydrogen carbonate. So now that I've established which 2 things I want to relate, now I can bring in the conversion or the numbers. The number in front of CO2 is 1. The number in front of sodium hydrogen carbonate is 2. Okay. I know moles of sodium hydrogen carbonate must disappear. So I'm going to place that in the numerator so that that unit can cancel. The number associated with it from my question was 1. And I would now see that I get 0.5 moles of CO2. Okay, neat. I've got to solve. But let's hold up here. Okay, remember how we did that bike example not too long ago? And we said we could either get 1.5 bikes or 2 bikes. And we said that our answer ends up being only 1 bike because we can't have half a bike and we couldn't make the 2 bike. Well, can I have half a mole of CO2? Am I allowed to do that? I couldn't have half of a bike. Can I have half of a CO2? We might need to listen to that phrasing once again. I can't, or can I have half of a mole of CO2? Can I have a molecule of CO2? Those are 2 different questions. One is a molecule, one is a mole. I cannot have, so not, have half a molecule of CO2 because the smallest indivisible piece for us is a single molecule. So a half a molecule of CO2 doesn't make sense. But a half a mole? Well, what is a mole? A mole was 6.022 times 10 to the 23rd molecules. Can I have half of, let's pick a number that's easier, 1,000 molecules? Yeah. So a half a mole is actually a valid thing. We can work with half a mole. We can't work with half a molecule. So again, this scale up to moles allows us to actually do some interpretations that we wouldn't typically be able to do at a molecule scale. And that's kind of neat. Okay, so we've got a new question here. How many moles of sodium hydrogen carbonate are produced when 1 mole of sodium carbonate, and this is by extension, 1 mole of water and 1 mole of carbon dioxide mix? Okay, so what I want you to go through and do is set up the work to solve that. Okay, that is a trivial one, but again, address the work. The work becomes important in this. Okay, and I'm actually not going to show it. Okay, so the next question. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? So this was similar to that if you only have 2 wheels question, because we're really only saying we're giving you just CO2. We got to be a little bit careful here. We aren't saying you just have 2 moles of CO2. We're saying 2 moles are being consumed in the context of this question. If 2 moles of CO2 are consumed, we had to have enough of the other 2. Okay? So we're actually assuming an infinite amount of sodium carbonate and an infinite amount of H2O, so that we don't have to establish a conversion that you did in the previous question. In this case, we can get away with just one conversion. Okay? So what is that one conversion? Well, what are we being asked to solve for? I want grams of sodium hydrogen carbonate. Okay? And now what am I given to start with? Okay, so again, we're given a lot of stuff. So I'm going to try and color code and simplify things. We're given 2 moles of CO2. And then we're also given this big honky chemical equation. Okay? So what I'm going to ask you to do is to see what you can come up with on your own here for a second, and we'll see you after you come back from hitting pause. That was the space button or clicking the pause button. Okay, so let's assume you're back. And maybe you were like, well, what the F, Mike? If I go through and look at this, I've got grams and sodium hydrogen carbonate. Well, the only place that sodium hydrogen carbonate shows up is in my chemical equation, but the measurement unit for that isn't grams, it would be moles or molecules. So I don't have in any of this explicitly given information the measurement of grams. Where do I start? Okay. Well, the easiest answer for me to go through and do is to start with the only place that you know. Okay? 2 moles of CO2 is using both a measurement and a substance that you don't want in your answer. So that's probably not a good place to start. The chemical equation does give you your substance. So I'm going to start with that substance and hope that if I work through this, maybe an answer falls out for where I want to go. So what do I want to relate this sodium hydrogen carbonate to? Well, the only other given information I've got, other substance, is CO2. So probably relating the moles of sodium hydrogen carbonate to the moles of CO2 is a good idea. The number values come from my chemical equation, the coefficients from there, and we've got that expression. We could then go through and recognize from that given piece of information, because this came from our chemical equation, in fact, our balanced chemical equation. So we've got that balanced chemical equation conversion in there. And now where do we want to go? Okay, well, I still don't know what's going on with the grams of CO2. Grams of sodium hydrogen carbonate. So I'm going to just leave that alone for the moment. I do know that I don't want moles of CO2, right? So the moles of CO2 are going to need to cancel with something. So I'm going to place moles of CO2 in the numerator and hope that somewhere moles of CO2 show up in the given. Oh, sure enough. There, in the given information, I know 2 moles of CO2. Okay, what is that being related to? It's not being related to anything. It's 1. Okay, so my moles of CO2 would cancel. Fantastic. That is great. I simplified it. I now have just the substance I want, but I don't have the measurement unit. Okay, so if we think back to the processing I've been asking you to go through and do, what we should now do is continue with that and just see if maybe we can get a clue by writing that information down on where to find this. I know I need grams of sodium hydrogen carbonate. And I know that needs to appear in the numerator because that's where it is in my answer. I also know that moles of sodium hydrogen carbonate needs to appear in the denominator so that that unit can cancel, right? So this conversion factor, I want to exist. Okay? I want the conversion factor that relates mass to moles. And if I have that, I have my answer. Based off of our last video, you should recognize that we do have that. That conversion factor is found on the periodic table. And what I can go through and do is sum up the masses for each of my individual species. And of course, I'm going to run out of room. Oxygen 16 times 3. And I would get that the mass is equal to a whopping 84 grams per mole. I could place that 84 into my calculation, grams per 1 mole. My units all now align and cancel out. All I have to do is enter this into the calculator, and my calculator spits out that I should end with 336 grams of sodium hydrogen carbonate if 2 moles of CO2 were consumed. Ta-da! This is the beauty of our process. As we move through, we're picking things that we've got and just trying to get them to work to fit this system. Okay? If you move through it slowly and address according to the methodology that I asked you to practice in Unit 2, this is now relatively straightforward, and the conversion factors that you need to find kind of fall out naturally from the process. If you've been fighting that process, you now have to be like, well, what conversion factor do I bring in? And you start slamming stuff into it and hoping it works. Sometimes it does, sometimes it doesn't. Okay? In that kind of slam things in, really what you're relying on is that you've done enough practice that you've effectively memorized an algorithm for how to solve. Okay? Not the best method, but it does work. Okay? This kind of question should look familiar to you because it is very similar to the question being shown here, which was on exam 2. Okay? And I usually get people on exam 2 being like, well, this question's entirely fair. There's no way I could answer this. Everything about this follows the process that we've addressed to this point, and even to the point in Unit 2. It allows us to solve. You just have to know how to manipulate those conversion factors. Again, according to the process that I've told you. Okay? What happens in this next unit, though, is that most of those conversion factors, you are required to derive and understand where they're coming from. So that question now becomes this. All of those conversion factors that were given to you, you have to be able to pull out of the context of the question. Okay? And that becomes challenging. Okay? So let's go through and address what is some of that context. So first context, oxygen gas reacted with hydrogen gas to produce water. We're being told a chemical equation. We need to know that oxygen and hydrogen are both diatomic elements. We would need to know the formula for water is H2O. We would need to be able to recognize that this equation is unbalanced, and we would balance it by placing coefficient 2's within that. This gives us a conversion factor that allows us to relate oxygen gas to the water produced in our question. Okay? Another conversion factor that we're going to have to pull out of this. Oxygen gas, since we know it is O2, we can go through and determine that it has a mass of 32.0 grams of O2 and 1 mole of O2. How do I know that? Because I know that relationship is found in the periodic table. I also need to be able to pull out the grams of water. I would need to recognize that 18.0 grams of water are found in 1 mole of water, also found by understanding the chemical formula and the periodic table. Okay? How do we put all of that together? How do we know we would need all of that information? Well, let's go ahead and clear everything away, and let's look at the question. What am I being asked to solve for? Grams of water. Okay? As far as given information, The only explicit given information is this grams of oxygen gas, which I could rewrite just because it's a bit wordy there, 9GO2, and there's our given information. Okay? We're also given this reacted with and this hydrogen gas, which should be a tip-off that we're looking at a chemical equation. Okay? O2 plus H2 to produce H2O. The chemical equation gives us conversion factors if it is a balanced chemical equation. So we would then need to acknowledge that we need, and actually it gives us conversion factors. Let's just address that for the moment. Okay? Do I need a conversion factor? Well, I'm given O2 as a substance, and I want to end with H2O. So am I converting a substance? Yes? Then yes, I need a balanced chemical equation. So I'm going to go through my process for balancing it. I can now go through and say, well, what do I want to do? Well, I know I need H2O as a substance. I know I'm given O2 to start. Where do I find the relationship between those substances? That comes solely from the balanced chemical equation. Okay, and the unit associated with that would be moles. I can pull coefficients from my balanced chemical equation, and I know I have 2 and 1. Moles of O2 is something I certainly don't want in my solve, so I could place moles of O2 in the numerator so that it cancels. But I'm not given the moles of O2. I'm given grams of O2. So if I'm paying attention, I don't want grams of O2. I could go through and say, well, if I can figure out this conversion factor, I could then drop the grams of O2 into my solve, and that would now cancel. Where do I find the conversion factor that relates mass and moles? That would be the periodic table. A single oxygen weighs 16. There are 2 oxygens in O2. My mass is 32 grams and 1 mole. If we're now tracking my units, because we've now got the ability to do some canceling, the moles of O2 cancel, the grams of O2 cancel, I'm getting dang close to my final answer, except if I compare, I've got moles in grams. So I need another substance conversion. In that substance conversion, grams needs to appear in the numerator, moles needs to appear in the denominator, and it needs to be for the substance of H2O. How do I know it needs to be for the substance of H2O? Well, because I wrote proper units, I can see that those substances need to be there. Well, where do I find the relationship again between mass and moles? That again goes to the periodic table with hydrogen with a mass of 1, 2 of them, oxygen with a mass of 16. This gets me to a mass of 18, and I get 18 grams of O2 is 1 mole, grams of H2O is 1 mole of H2O. The moles of H2O do a long distance cancel, and if I now track all of my units through this given process, I now have the ability to go through and solve. What does that solve come out to be? A whopping 10.125 grams of H2O. We should consider sig figs. I know I've actually been avoiding that question. We get 3 sig figs because we were given 9 grams to start, which is 3 sig figs. So 10.1, the 2 and the 5 are going to be insignificant, and our answer becomes 10.1 grams of H2O. Because you might have a question and say, well, aren't there sig figs in our individual conversion factors? Okay. Say from our balanced chemical equation, the balanced chemical equation has infinite sig figs. Okay, those are defined units for those. The molar mass conversions that are coming from your periodic table don't have infinite sig figs, and those could control your answer. Okay, because those are things that you're looking up to calculate. What you should go through and do is ensure that the number of sig figs in those conversions is larger than the number of given sig figs. Okay? In this case, I didn't really do that. I did some rounding, but that rounding actually doesn't have an effect here because of where the molar mass of oxygen and hydrogen are. Okay? And we now have our entire process with all the nitpicky details and pieces associated with it. Okay? So all we're really doing in chapter 9 is introducing that new conversion factor that we've got in purple, which is our chemical equation. How do we relate substances to each other? Okay? When we relate substances, it has to be the same measurement, and that measurement unit is a counting unit, either moles, molecules, atoms. Okay? It is not a measurement as in grams, milliliters, liters, any of that kind of stuff. Okay? So we're going to end this with just a bunch of kind of summary slides. Ultimately, what we're trying to push to is dimensional analysis. Okay, why? If you have to take more chemistry, dimensional analysis is what you're going to do. Every chemistry instructor is going to expect you to be able to do dimensional analysis. Okay, you don't need dimensional analysis, again, because you don't have chemistry. You're probably wrong. Okay, what you'll end up doing is having an algorithm given to you to force your conversions. Okay, so that you don't have to think about it. If you're planning on going into nursing, one of the tests in nursing is to do a bunch of conversions, because conversions matter when it comes to how much drugs you should be giving somebody. And if you overdose them and they die, that could be your liability. So they ensure that you know how to do conversions. Okay, so you'll see it show up again. How important is it then? If you fail that test, you're out of the nursing program. Okay? So if it took you 5 years to get into the nursing program and you fail the test, you can still become a nurse. You just have to wait another 5 years of application cycles to get back in so that you can retake that test. Okay? Different institutions have different requirements behind that test, but as far as I know, all institutions require that conversion analysis because it is of critical importance to giving drugs to patients. Okay? The beauty of dimensional analysis beyond nursing, science, or any of those is that this process works all the time, every time, for everything. There's not a single thing that it doesn't do well for. Okay? So if we go through and look at our general process again, what we've got here is this desired. This is our want. This is our have. When we go through to convert, we want the have in the denominator. We want the want in the numerator. Those wants and haves may change. We may have multiple iterations, but those are allowing us to do those conversions. So identify what you want, identify what you have, want over have, every single time. It'll work. Okay? We got the equalities for that. Okay? Y given in that format. That equality allows us to convert A to B or convert B to A. Okay? Where are those conversions? Where did we get them from? If they're measurement conversions, those measurement conversions are ultimately all chapter 2 stuff. You'll find it in the textbook, on your exam, or in your brain. Okay? In our chemistry conversions, we got a lot of conversions listed out down here. Going atoms to AMUs can come from the periodic table. AMUs to grams ends up being a weird, goofy conversion if you wanted to use that. You can do periodic table, molecular mass, grams to moles. Moles to moles come from a balanced chemical equation. Okay, so all of those conversion factors allow us to manipulate and convert between them. If you don't know where you're going, you're just throwing conversions at it and hoping it works. This is why you use dimensional analysis. It always keeps that end goal in mind so that you know which things that you should be attempting to do. Another way to look at our conversion factors is just where to find them. They're all kind of listed out here. Again, it's just another format for how you could potentially see and go about finding these things. Okay, so with that, there are tons of practice questions for dealing with moles and mass in the mole chapter, chapter 8, and then tons of conversions dealing with substance conversions, or chemical equations, in chapter 9. you should be going through and looking at those, because we're going to make them more complicated by looking at different ways that we can measure these things. At this point, all I'm asking you to do is say we're measuring by mass. How can we get these into units that we can manipulate through a chemical equation? In chapter 8 and 9, they reference volumes. I don't want you looking at volumes yet. Okay? That is going to happen very, very fast here. But I want you to be careful when addressing volume measurements, because there's different ways we can deal with those. Okay? And that's going to be the next probably 2 lecture videos. One on volumes from solutions and one on volumes from gases. With that, I'm going to go ahead and stop and give you time to hopefully absorb and practice this.